Hello, thank you for visiting. This is NOBsLABO. In this video, I will use 3D animation to explain quantum entanglement and Bell's inequality in more detail, especially using the photon polarization phenomenon adopted in the Nobel Prize experiment. I would like to analyze from the perspective of probability theory what Einstein meant by spooky action at a distance, what was wrong with classical physics, and what we can learn from the violation of Bell's inequality. You can also see the concrete experimental results in YouTube videos such as QUED entanglement demonstrator. Let's get started. This shows linearly polarized photons. The arrows indicate the polarization angle. If the polarization angle of the photon matches the polarization filter angle, 100% of the photon will pass through the filter. Tilt the filter 90 degrees and all photons will be blocked by the filter. If the filter angle is 45 degrees, 50% of the photons will pass through and the polarization angle will be the same 45 degrees. If the filter angle is set to 22.5 degrees, which is 1/4 of 90 degrees, about 85% of the photons pass through the filter. If the filter angle is set to 67.5 degrees, which is 3/4 of 90 degrees, only about 15% of the photons pass through the filter. This relationship is shown in the graph. The passage rate is not proportional to the angular difference and is represented by a cosine squared curve. This curve can be derived from the theory of electric field vectors. Light is a spatial oscillation of the electromagnetic field. For linearly polarized photons, the electric field oscillates in only one direction. A polarizing filter only passes through light components which vibrate in the filter direction and reflects or absorbs all orthogonal components. Let's consider the case where the linearly polarized light is tilted by theta degrees. Due to the vector nature, the magnitude of the electric field vector becomes cosine theta times larger. When the voltage increases by a factor of cosine theta, the current also increases by a factor of cosine theta. Brightness is calculated by voltage x current, so it is cosine squared theta. Since brightness is proportional to the number of photons, the passage rate will also be cosine squared theta. Next, I'll show you what happens with unpolarized photons. As an example, sunlight is unpolarized. Unpolarized light can be considered to be a superposition of light in all polarization angles. When the photon hits a polarizing filter, this superposition state collapses and changes to linear polarization in the filter angle. Although the waveform is random, the direction of the electric field is limited to a single plane. And we can show this as an animation of each photon. The semi-transparent disks represent the random polarization angles. This unpolarized state collapses when the photon hits the polarizing filter, and 50% of the photons pass through the filter. One important point is that the probability of passage is 50% for any filter angle. Next, install a second polarizing filter on side A. An unpolarized photon will pass the first filter with a 50% chance and pass through the second filter as a linearly polarized photon. In this case, if the angle between the two filters is theta, the probability of passing through the second filter is cosine squared theta. Now that we are prepared, we will move on to the explanation of the case where a pair of entangled photons is used. To make it easier to understand, we will first explain the behavior of photons based on the currently mainstream Copenhagen interpretation. After that, I'll show you what Einstein found problematic about the behavior of the photon, and then I'll show you how that problem was resolved. What we are showing you is an animation of photons based on the strong Copenhagen interpretation, which is currently the mainstream. A pair of entangled photons is simultaneously output from emitter A and emitter B. The purple spiral represents the quantum entanglement. Entangled photons are always unpolarized. When a photon hits the polarizing filter on side A, its polarization state is collapsed and it passes through the filter with a 50% probability. In the Copenhagen interpretation, when a photon on side A collapses, the entangled photon on side B also collapses. The polarization angle of the photon on side B will be the same as the filter on side A if the photon passes on side A, and will be perpendicular to the filter on side A if the photon is blocked on side A. However, it is just an interpretation, and you cannot visually confirm the collapse of photons on the B side as shown in the last animation. What can actually be observed is the pass block result obtained on side B by passing the photon through the installed filter. A pair of photons that pass the A side filter will pass the B side filter with 100% probability. A pair of photons blocked by the filter on side A will always be blocked on side B as well. So why do we think that such photon collapse occurs in the Copenhagen interpretation? This is because the photon passage rate is cosine squared of the angle between the filters, just like when a second filter is placed on side A. If this is the case, we can only assume that the B-side photon has already collapsed to the same linear polarization as the A-side photon. However, Einstein had serious doubts about this phenomenon in which the collapse of the polarization angle of the photon on side A appears to be transmitted instantly to side B. The two filters can be separated by tens of thousands of light years. Even so, the polarization angle is immediately transmitted to the other photon, and the assumptions of the theory of relativity seem to be broken. Einstein called this hypothetical information transmission faster than the speed of light, spooky action at a distance. However, during his lifetime, any experimental verification of this strange action could not be realized. But Einstein was aware that the quantum equations contained this strange action, and he suspected that quantum mechanics was still incomplete. At the same time, Einstein also suspected the indeterminacy of the polarization angle of unpolarized photons. In fact, he believed that the behavior of photons when they are collapsed by a filter is determined in advance, but we simply do not know yet the laws behind this. Below, we will look at two classical physical models that appear to be able to explain quantum entanglement, and assume the deterministic physical model Einstein believed in. The first classical physical model assumes that unpolarized photons have polarization angle information as an internal parameter. In this animation, the hidden internal angle is shown by an arrow inside the transparent disk. Polarizing filters have an internal blocker that passes only photons with internal angles within a range of plus or minus 45 degrees from the polarization angle. We also assume that the internal polarization angle of each entangled photon pair is the same. Then, for example, if the polarizing filters on sides A and B are at the same angle, the paths blocks of the entangled photon pairs will be perfectly consistent. This matches the results of the actual experiment. Also, if you tilt the filter on the B side by 90 degrees, the blocker holes will no longer overlap, so no photon pairs will pass through A and B at the same time. Setting the angle of the filter on side B to 45 degrees halves the area of overlap of the holes, so that 50% of the photon pairs pass through both filters. Furthermore, even if the filters on sides A and B are rotated by the same angle, the overlap of the blocker holes is the same, so the transmission rate does not change. Unfortunately, this is the last point where this model agrees with experiment. For example, if the angle between the filters is 22.5 degrees in this model, the overlap area of the two blocker holes is 75%, so the passage rate will be 75%. But in case of entangled photons, the probability of passage is a cosine squared, so the matching rate of the passing photons must be about 85%. In fact, in this classical model, the coincidence rate between photons is always proportional to the angular difference between the filters, which is inconsistent with quantum entanglement. If this is the case, by thinking the other way around, would it be possible to explain the quantum entanglement making the probability of passage be cosine squared? In this second classical model, the polarization direction of both photons is aligned along the x-axis or y-axis and output alternately from both emitters. If both polarizing filters are aligned along the y-axis, then any photon pair aligned along the y-axis will pass both filters. Also, if the filter on the A side is aligned along the y-axis and the filter on the B side has an angle of theta from the y-axis, the cosine square of the angle is the coincidence rate of photons that pass. This passing probability perfectly matches the entangled photon pair. So, is there a classical physical model that can explain the quantum entanglement as Einstein predicted? For a further confirmation, let's rotate the filters on both sides and align them at 45 degrees from the y-axis. In this setting, because the photons are polarized along either the y or x-axis, when they pass through a 45 degrees filter, 50% will pass and 50% will be blocked. However, there is no way to synchronize the pass or block of photons on both sides. Therefore, the pass-block rate of photons cannot match perfectly between sides A and B. This is different from the results of quantum entanglement experiments. The quantum entanglement model requires angular isotropy, but the second classical physics model does not satisfy this requirement. In the first classical physics model, if the filter angles were equal on both sides, the transmission of the entangled photons could match exactly. However, if there was an angle difference in the filter, the passing probability became proportional to the angle difference, and it was not possible to realize the cosine squared transmittance characteristic of quantum phenomena. In the second model, we were able to achieve cosine squared transmittance by setting the polarization direction of the photon pairs to the same x or the y-axes alternately. But we found that there was no isotropy when the both filters were declined from the y-axis. Bell sought to determine the transmittance conditions that a classical physics model must satisfy against 3 different filter angles, and to prove that quantum phenomena are within the scope of classical physics, and that a classical model capable of expressing them must exist. In addition to 0 degrees and 22.5 degrees, we set up a polarizing filter at an angle of 45 degrees and test whether it passes through. Let's call each test pass as alpha, beta, and gamma. Randomly select 2 tests from these 3 and set them to the A side and the B side. Check the pass or block of each side and summarize it in this set diagram. In this case, the probability inequality shown on the right holds. A bar with a red line represents a test failure. This inequality is called Bell's inequality. The first term of inequality is the probability that one of the photons in the pair will pass through the alpha filter and the other will be blocked by the beta filter. This is represented by the blue area in the set diagram on the left. The second term of inequality represents the probability that one of the photons in the pair will pass through the beta filter and the other will be blocked by the gamma filter. This is the red area in the set diagram on the left. The right-hand side of the inequality is the probability that one photon will pass through the alpha filter and the other photon in the pair will be blocked by the gamma filter. This is represented by the purple shaded area in the set diagram on the left. As you can see from the set map, the purple area is completely contained in the red and blue areas, so the probability should always be equal to or less than the probability of the red and blue parts added together. Actually, there is one trick in the aggregation of this Bell's inequality. For example, if you want to find the probability of the first term from 2 filters, alpha and beta, since we don't know the pass or failure of the gamma filter, we cannot separately find the probabilities of the light blue and dark blue parts of this figure. However, in Bell's inequality, all you need to know is the probability of combining these 2 parts. Even if you don't know the ratio of light blue to dark blue, you can accurately calculate the probability by following this set diagram. And if the aggregated data from the passes and failures of the alpha, beta, and gamma filters can be represented in this set diagram, then Bell's inequality should always be satisfied. Now, let's see if this Bell's inequality actually holds. In order to make the calculation easier to understand, I will write the conditions to block by changing the setting angle. Advancing the angle of each filter by 90 degrees reverses the occurrence of the pass and block. For example, a photon that passes through a filter on a alpha bar is a photon that is blocked by a filter on a alpha. This allows you to think of the conditions of the block as the angle at which they will be passed. This is the case of the internal direction model with a wedge-shaped gap in the blocker, introduced first. The alpha and beta bars are 112.5 degrees apart, so the coincidence rate of photons passing through is 25%. Half of the input photons are blocked by the filter, so the photon pairs that pass through are 12.5% of the input. The beta and gamma bars also have the same 112.5 degrees difference, so the photon pairs passing through are 12.5% of the input. Since the alpha and gamma bars are 135 degrees apart, the photon pairs passing through are 25% of the input. Hence, it satisfies Bell's inequality. Now consider the case of the second classical physics model. In this model, both emitted pairs of photons have a 50% chance of having the same 0 degrees polarization angle or the same 90 degrees polarization angle. If the polarization angle of the photon pair is 0 degrees, the filter with alpha angle will pass 100% photons, and the filter with the beta bar angle will pass photons with a 15% chance. And in the other case, when the polarization angle of photon pairs is 90 degrees, one of the photons will be blocked by the alpha filter, so no pairs can pass through. 50% of emitted photon pairs have a polarization angle of 0 degrees, so the probability of the first term of Bell's inequality is 7.5% by having the 15%. In the calculation of term 2, the probability is 42.5% by calculating the product of the probability that a 0 degrees photon will pass through the beta filter and the probability of passing through the gamma bar filter, and the product of the probability that a 90 degrees photon will pass through the beta filter and the probability that it will pass through the gamma bar filter is 7.5%. By averaging, the probability of the second term is 25%. The probability of the right-hand side of Bell's inequality is 25% by the similar calculation. So we can see that Bell's inequality is also true in the second model. What about photon pairs that are actually in a quantum entanglement state? Since the alpha and beta bars are 112.5 degrees apart, the match rate in this case is 15%, which means that 7.5% of the input photon pairs pass through both filters. Similarly, the passage rate of beta and gamma bars is also 7.5%, because they are 112.5 degrees apart and the submittance rate is isotropic. Now we can see that Bell's inequality is broken. Classical physics model 1 is made so that the probability of passage coincidence is isotropic for simultaneous changes in filter angles on both sides. However, the relationship between the angle difference between the filters and the probability of passage is proportional and cannot be made into a cosine squared. As a result, the probability of terms 1 and 2 is 12.5%, so it cannot violate Bell's inequality. In classical physics model 2, if the filter on the A side is alpha, i.e., 0 degrees, the probability of passing is cosine squared, hence it is 7.5%. Though if you increase the filter angles on the both sides by 22.5 degrees, the transmittance probability will change to 25%. Even though the angle difference between the A side and the B side filters is the same as in the first term, 22.5 degrees. The probability change is not isotropic, which results in Bell's inequality. On the other hand, in the case of actual quantum entanglement, even if the angle of the filter on the reference, A side, is changed, the probability of passage for the difference in the angle of the filter is always cosine squared, so it can break Bell's inequality. But why is this breaking of Bell's inequality so serious? Breaking Bell's inequality means that the test results of alpha, beta, and gamma are not independent. This means it is not possible to add gamma results to the set diagram as shown in this figure. Testing gamma changes the results of the alpha and beta. If a gamma filter is sandwiched in front of a alpha or a beta filter, for example, then one photon will pass through the gamma and alpha or beta filters, so it doesn't matter if the gamma test changes the results. However, in quantum entanglement experiments, the gamma filter is always set on a different side from the other filters, so the addition should not affect the set diagram of the alpha and beta. Thus, the violation of the Bell inequality indicates that filters in separate locations affect each other. This is a phenomenon that cannot be explained in classical physics. Spooky action at a distance is real in the quantum world. If the results of quantum entanglement experiments satisfy Bell's inequality, then quantum phenomena should be able to be described by models of classical physics. If that were the case, the spooky action would not have existed and the Copenhagen interpretation would have needed to be revised. However, the results of quantum entanglement experiments have violated Bell's inequality, demonstrating that quantum phenomena go beyond the scope of classical physics, and the 2022 Nobel Prize in Physics has been awarded to Alain Aspect and others. Then, can we actually use quantum entanglement to instantaneously send the filter angle information on side A to side B? Again, I'm showing you the imaginary animation based on the strong Copenhagen interpretation. If you know whether a photon on the A side passes or is blocked, you can calculate the angular difference between the filters by summing up the passage probabilities in each case on the B side. However, if the passage of photons on side A is completely random, it is not possible to separately count the passage probabilities of photons on side B. As a result, side B can only obtain a 50% pass probability, which is the average of 85% and 15%. Since the brightness of unpolarized photons is always halved when passing through a polarizing filter, no information from side A is obtained on side B. However, Einstein also doubted the randomness of the photon passage. If there is a law here, and side B can predict the passage of photons at side A, then information will be transmitted from side A to side B at a speed that exceeds the speed of light. Fortunately, even today, the collapse of quantum states is thought to be completely random. Spooky action at a distance was proven, but the assumptions of the theory of relativity were not overturned. That's all I want to show you today. When we try to understand quantum mechanics, we are reminded how much our understanding is bound by the logic of classical physics. For example, when you see an animation in which the collapse of the polarization direction of a photon on side A appears to be instantly transmitted to a photon on side B, it seems as if communication faster than the speed of light could be realized. But this is only possible if we know, on side A, whether the photon passed the polarizing filter or was blocked. In quantum mechanics, this transmittance is random and unpredictable. Moreover, the pass or block of the photon on side A is not only unpredictable, but also uncontrollable and unenforceable. This means that side A cannot control side B through quantum entanglement. If we misunderstand the animation of the Copenhagen interpretation in the classical sense, It seems like we can control an entangled world in an instant. However, in reality, we cannot control the collapse of the wave function even on our side, so we cannot control the opposite world. Einstein said, "God does not play dice," but in fact, God plays the dice in order to realize the quantum entanglement on which the world is constructed. How carefully this world is crafted. This video was firstly created to supplement my own memories, but if you have any comments or suggestions, I would be grateful. See you in the next video. Bye.